All right, folks. Um, as we get started today, I want to begin just by making sure that you kind of have a concept down. It's going to be something that's vital to our ongoing, what we end up doing here, and I want to just kind of make sure you have this. Um, so we've been talking about we've sort of thrown around the idea of the mole, and we know that a mole. I'll write it up here. Um, one mole equals 3.02 times 10 to the 26th. All a mole is a number. Okay, it's a big number, a really big number. That's a lot of. Um, why did I put three? It's not three. It's too early in the morning. It is not three. It is 6.02 times 10 to the 23rd. So I'm going to change that. Oh, I see what I did. I inverted that. So it's 6.02 times 10 to the 23rd. I'm sorry about that. Okay. 6.02 times 10 to the 23rd. That is what a mole is. Now, how is that significant? You that number in and of itself isn't really going to be significant to you, but I'm going to explain to you how we got to that number. Okay. So, I'm going to take this and kind of set it aside for a second. And I'm going to be like, okay, let's look at the periodic table. So I'm going to switch over to the periodic table here. When we switch over to the periodic table, I'm going to look at, in particular, I'm going to look at copper. So there we are looking at copper. So I can ask you, what is the atomic mass of copper? And you would say it's 63.55, rounded to that, 63.5 if you want to round it to there. So about 63 and a half. So what does that mean? So what that means, I'm going to flip back over here. So atomic mass, um, atomic mass, and let me do copper in particular equals 63 point, I'm going to use 63.5 AMU. So that means, and let's flip back real quick over here. That means it has, up here in the top, I see my atomic number. So it has 29. So we have 29 protons. 29 protons. So I have 63 and a half minus 29 for neutrons. So neutrons are going to be 34.5 neutrons. Now you can't really have 0.5 neutrons. What happens is that on average, so you have some with 34 neutrons, some with 35 neutrons. On average, that's what you're going to have. So this is going to be like on average. And any sample of copper that we have, that's what we have on average. So that tells us, that's how we get our mass. So, a proton is one mass, a neutron is one mass, and a electron we don't worry about because the mass is so small, we count it as zero. So this is how we get our atomic mass for copper at 63.5 AMU. Now, here's the big difference, okay? The key is that one proton equals, so this is one proton or one neutron. We're counting them as the same. They're almost the same. 1 over 6.02 times 10 to the 23rd grams. That means if I had 6.02 times 10 to the 23rd protons, that would equal 1 gram. You see what I'm doing there? A proton is this. That gives you that will give you like the size of a proton or the mass of a proton is that. So this still seems kind of weird, right? Like, what does this really mean? So that many protons is equal to 1 gram, which means, think about this, which means if I had 6.02 times 10 to the 23rd copper atoms, I'll put atoms here, what would that weigh? And it's actually really easy. It would weigh 63.5 grams. So I'm going to put that in here, 63.5 grams. So in essence, it's a way for us to be like, oh, like we did the math and figured out, oh, you know what? These numbers, I'm going to go back over here. These numbers on your periodic table, these numbers aren't just the atomic mass units. They're also the number of grams that 6.02 times 10 to the 23rd atoms of any of these elements would weigh. Okay? That's what we kind of figured out. And so I can make sense of this. Like right here, I have this is copper. I think you can see the color, kind of tell hopefully that it's copper. And it's actually a sample of relatively close to, like it's hard to individually count these, right? But it says on there 1 mole of copper. Actually, it doesn't even tell me it's copper. It just tells me that it's 1 mole. I can figure out that it's copper. If I know this is 1 mole, I can put it on a scale and weigh it. And you know what? I've weighed this before. It weighs about 63.5 grams. So that completely makes sense. That's what the mole is. The mole lets us go from AMU and talking about individual atoms and individual molecules to talking about grams of molecules and talking about like something we can actually physically handle, touch, feel, all that kind of stuff. So that's the whole purpose of the mole. The mole the mole just gives us a big number that makes us be able to translate back and forth. You could also, let me give you another illustration. So this is a piece of copper. It's got 6.02 times 10 to the 23rd atoms in it, and therefore it weighs about 63 and a half grams. Okay, so let me show you what a mole of aluminum looks like. So here's aluminum. The aluminum is bigger, right? Hopefully you can see that. Do it like that. The aluminum right here is bigger. Why would the aluminum be bigger? So I look at it, and the aluminum is bigger, and it weighs less too, right? So let's look over here at aluminum right there. So 6.02 times 10 to the 23rd atoms. The atoms, remember, are going to be larger because you're moving across the periodic table. They're also going to be way less because if you look at the aluminum, you have less protons and your mass is 26.9. So if you weigh this weighs about 27 grams. This weighs 63 and a half grams. So I could weigh this if I didn't know what it was, and I could probably figure out what it is because it'd be pretty close to a mole of aluminum atoms. Okay. So I have other samples here. I have steel, or not steel, I have iron, and I have zinc. Same thing. You can look up on the periodic table and tell. Now, the other thing we can do is look up on the periodic table and see, like, carbon right here is 12. Oxygen right here, 16. Hydrogen, 1, right? So that gives us the weight, or the molar mass, we call it, the mass or the weight of a mole of those atoms. So when we have, so let's go over here and just take a look. I want to first erase this. How do I erase? Let's do this. Erase. Let me erase all that so I have a little bit of room. And okay. So let's go here. I'm going to stay with, I'll go with like a lavender or something. Okay. Let's take a look at our document here. So we are, first of all, going to balance this. So when we balance it, we have 6 carbons, 14 hydrogens. I can tell you already, like if we do this, so I go 6 carbons, I'm going to put a 6 here, balancing the carbons, 6 and 6. I would encourage you to just keep doing the process like this, because we're almost done with this. And don't try to skip ahead, because you get yourself in trouble really fast. Hydrogen, I have 14 over here. I want to have 14 over there if I put a 1 in front of here. So I'm going to put a 7 here. Now I have 14. Oxygen, starting on the right-hand side, I have 12 plus 7. That's going to be 19. That's not going to work. So I'm going to go back up here, change this to a 2. That's going to make this 12. Change this to 12. It's starting to get messy, isn't it? I don't want to erase it because I want you to see my process. This hydrogen is going to be 28. Over here, that 7 is going to change to 14. This oxygen is going to be 14. This oxygen, oh no, that's not going to be 14. It's going to be 14 there, plus 24. 14 plus 24, 38. Half of 38 is 19. So there's my balanced equation. I'm going to put my 19 here. Okay. So I have my balanced equation. I can go through and do my ratios. That's hexane up there. Hexane to oxygen is 2 to 19. Carbon dioxide to hexane, 12 to 2. Oxygen to carbon dioxide, 19 to 12. Water to oxygen, 14 to 19. Carbon dioxide is 12 to water is 14. Water is 14 to hexane. Hexane is 2. Okay? So there's all my ratios. And now, remember last time I said I have a given number of moles of, let's say, of hexane. This time, instead of moles, I'm given 650 grams of hexane. So all of this up here is in moles. All of the whole formula up here, this is all in moles. My ratio is all in moles. And we saw that things can weigh different amount. A mole of something doesn't always weigh the same. So I can't just take the masses and make them equate. I have to change to moles. So when I change to moles, I go, all right, how many moles, if I have 602 grams of hexane, so 602 grams of C6H14, how many, what am I asking here? How many moles of CO2 would I have? So the first thing I got to figure out, how many moles of hexane do I have here? Okay. So in order to find that out, I have to add up the molecular mass of each of the components to find out how much 1 mole of hexane weighs. So carbon, let's look back over here. We'll find the mass of carbon and we'll find the mass of oxygen. So carbon we looked at, carbon is 12. So 12.011. So I'm going to say 12. Hydrogen over here is 1.008. I'm going to say 1. Okay. So 12 and 1. So let's go back over here. Carbon is 12. How many carbons do I have in each molecule? I have 6, right? So I'm going to go 6. 6 times 12, 72. So hydrogen is 1. How many hydrogens do we have? Go back over here, right there. We have 14. 14 times 1 is 14. So this should not give me moles here. Sorry. That's 1 mole of hexane. So 72 plus 14 is going to be 86 grams per mole. So 1 mole is 86 grams. So the way I figure this out is that I got to go up here and go 86 grams. So I'm going to divide 602 by 86 grams of C6H14. I'm going to do that because I'm trying to find out how many moles I have. I know I have this many grams. I'm going to divide by how much 1 mole weighs. So I got 602 divided by 86. And that tells me that I have 7 moles of C6H14. 86 times 7 is 602. So now I know that I have 7 moles. I'm right back where I was just the other day, right? That we already did this part. So I'm going to go down here and I go, all right, I want to find out how many moles of CO2 I have. So I go, how many moles of hexane do I have? I just figured it out, right? I have 7. So I just put, I have 7 right there. When this is the ratio, remember, right there. So this is the ratio of CO2 to hexane. So if I go back up in my problem, CO2 to hexane is 12 to 2 right here, right? Remember this one? Boop. CO2 is 12, hexane is 2. If I go down, if I do this, and remind you, up here, CO2 is 12, hexane is 2. So that means I can go down to here, and I'm going to put a 12 on top, 2 on the bottom. So now I have a fraction with a 2. 7 times 12. So if 6 was 72, that's 82 plus another 2, that's 84, right? So 84. So I have 84 over 2. What's 84 divided by 2? That's 42 moles of CO2. And that's what I was trying to figure out, right? Here's how many moles of CO2. So my given is right here. My given is right here. And here are my moles of CO2. So literally the only thing that we've added in this whole entire process, hopefully a little better understanding of the mole, the only thing we've added is this process right here where we convert, and I'm going to go down here too, in this fraction up here, where we convert the grams of the substance. We divide those grams by the molar mass of the same substance to get moles of the substance. That's the equation that we're doing. And that's all you really have to, that's the only thing new that you're applying to this aside from what we've already done. Okay? So hopefully you have no problems on our little worksheet we have today.